As if there was any doubt about what I was going to talk about. Okay, so I have to say that I had prepared this for 2 hours. What we have are 40 minutes, and I guess even less than that, 35 minutes. So I'll try to rush through the parts which I find not so interesting. How I want to do it right now is I would talk about two different sections. Then I had a bunch of examples for eBPF usage, which I'll skip through, and then at the end I have a small demo for what Dushyant and I have been working on. That is something which is eBPF based, that is in production and is used by a large number of clients at Red Hat right now as well. Okay, so I'll start by negating everything that you have heard since this morning. Wow, this is a very bad font. It wasn't looking like this, but let me read through what it said. Is eBPF all good? We've worked through eBPF. We now know what eBPF is. We have almost all of us have at least run one program in it. We have tried. We know what it does. Question is it all good? I'll just read through it because it might be difficult. It's a quote by Brendan Gregg, who is attributed to be the person who is responsible for eBPF being in existence. It says as eBPF has many uses in improving computer security, but just taking eBPF observability tools as they are, and using them for security monitoring would be like driving your car into the ocean and expecting it to float. So it's not all good. There are a few issues that readily need to be tackled. I'll talk about 4 different issues. The first of which, as almost all of us faced since we started working on eBPF this morning, portability. I have kernel 6.2, I have 5.19, I have 5.2, I have 5.14, and everybody had different issues. Some we had issues with what we are going to, which are the include files that are required. We had issues with which are the functions that run in one case versus the other. So portability is an important aspect to make any technology useful, and it's very important for something like eBPF, whose task is to where the main goal is, we want to do some observability. So I'm not going to observe what's happening on my laptop, right? It's going to happen all across the world, across different VMs, across different systems. Portability, obviously, one of the issues. The second one is toolchain. Again, Dushyant talked about it. There are a number of moving pieces when you are running through running an eBPF code, and each one of them have to be perfect in its own way for the entire toolchain to work. Third one, which is very important, which you will face when you start doing things on your own, there is lack of documentation. And the fourth one is self-explanatory. It's relatively new, so people who know it, they also know a subset of it. Dushyant and I have been working on it for a few years, but still, whenever there is a new thing that comes up, it's difficult to find examples. It's difficult to find use cases where that certain thing could be used, or whichever problem we are facing. So these are 4 basic development level problems that exist with eBPF in the current scenario. We kind of have a solution for one of them, one or two of them for that matter, which is called BPF Core E. It's not BPF Core, but it's rather pronounced as BPF Core E, which is BPF compile once, reuse everywhere. So CORE. As you must have realized by this time, a technology like BPF does require it to be Core compatible, and this is again a newer concept than eBPF. And I will just try to go through things and see and explain what the problem is. So this is how this is what we've been all doing since today morning, right? Production server, what we do is we have the application, you are doing the compile, you're running the make, it's running clang, then it takes your eBPF.c code, it includes the system headers, create that object file, and eventually you go into the kernel where you have a running eBPF code where which works through. Now the problem here is, I'll show you a very small snippet of code here. I don't want to get into the details of it, but just looking at maybe the name of the function. Does anyone want to tell me what this function is doing? It's written on the slide. It's written on the slide. It's trying to get the namespace ID of the kernel which is currently mounted. Very simple. If you look through it, there is one function, there's one structure which is doing the read kernel, and the next one is just returning the I number or the ID of the kernel that was read by the first one. Now, in the current scenario where the way we were developing it since morning, this is how we would write this code. To make sure that it runs across my system, your system, and everybody else's system, we'll write multiple if conditions there. If my kernel is this, run it through this version. If my kernel is something else, I'll go through the other version. In this case, for 414 through 418, you are running it in one way. Okay, I can do this. For 419 onwards, you require something else to run. But the problem is, this is not the ideal case, right? You have multiple versions, you have minor versions, and you cannot keep on changing your code for everything and anything around here. In comes, okay. So what we would ideally want is, I just write these two lines, and inside eBPF is able to understand what this means, where to get this exact number from, and be done with it. Okay, I don't have a lot of time, so I'll probably just go by these things, go by this quickly. But on the fly, BPF compilation is something that seemed very relevant at some point. Seemed really relevant when you consider the kind of problems that we've been having. Okay, we need the access to kernel structures because you want to understand where this inode is, what is the exact value that we require. In the previous case, it was the namespace ID of namespace ID of the mounted kernel. Across multiple versions of kernel, obviously the memory layout changes. There are many other things, tiny little things which change, which you as a developer cannot really keep track of because there's just so many moving pieces, as I said. And the other problem, which is on the right side of your slide, if you see, not every machine really is equipped to do the compilation of the kernel. You require multiple libraries, you require these heavy codes which not all kernels and not all machines have the access to. So we have what we call, as I said, BPF CORI, which is compile once, run anytime flow. The top layer diagram that you see there, it's the development server and what happens in there. I'll try to explain each of these individual items as quickly and as in as concise manner as possible. So the first thing that you see is something called the kernel BTF. Turn on the laser. Okay. So the first thing that you see is something called the kernel BTF. Kernel has a section called BTF. BTF is BPF type format. I'll quickly show you what this is. Then through the BPF tool, you have access to the VM Linux H, which is the headers for the current kernel that is working on. Then you have your eBPF.c, the actual BPF code that you have written, including the C, and then you compile it over CLang and create something which looks like this. The BPF.o, which is an object file with an additional section there called relogs or the relocation information. Now it's packaged and then sent into wherever this code needs to run. At the production server, where the actual code needs to run, this application, which has the bpf.o, the object file in there, is read by the loader, which is the libbpf. Libbpf is a library, a dynamic library that supports your BPF functionality. It reads through the BPF object file, goes through the relocations, adjusts the relocations or the pointers according to the current kernel where it is running, with the kernel information, which is where it has the BPF type format information, and eventually loads on it to the kernel and runs. So this is the total lifespan of when you use BPF with CORI. So in simplest words, what exactly do we want? We want to write eBPF code without really worrying about kernel differences. We want the freedom to distribute without knowing what is the target kernel in the running machine, and not really have to rely on one specific kernel feature. This kernel supports this specific thing and that's why my code runs, otherwise it does not. It should not be the case because production systems don't work like that. So when we have Cori, okay, I'm trying to see how quickly do I have to go through things. But there are 4 different parts to the Cori infra that we saw here, right? We have the BTF, which is a very important part of the Cori infrastructure, the Cori mechanics, which is the BPF type format. Then you have the compiler, the actual compiler, the CLang in this case, which creates the object file with the relocations attached to it. Then we have the loader, which actually loads the information and sets everything according to the current kernel. And then we have the final kernel, which runs where the BPF code goes and attaches to and runs. I'll probably just skip over this. Skip over this as well. Because I just don't want to get into details because you'll have, we won't have time to complete the rest of the things that we wanted to. Extending kernel functionality is, okay, so till this point, my assumption is that you have some, at least on an abstract level, an idea of what BPF Cori is, what is it used for, and conceptually how does it work. Really how it works is slightly different. So if you want, I can give you this one quick example where we have this task in the left side, you have a BPF code which does some things, and it's trying to read the number of bytes in this task. Now, depending on what kernel it is, where these number of bytes are stored, what is the exact offset might differ from kernel 6.2 to 519. What the field relocations give you is that this is a task, this is the structure of task struct, and we want this particular element within it. So what the loader, when it's loading, would add this value. So in this case, if you see, the instruction number 1 here is the R0, which is the register 0 gets appended to the value 1952, which possibly is the pointer to where this value is actually stored. There is no way as developers we can know this information beforehand. It has to be calculated on the runtime, which is what Cori does. So in order to extend kernel functionality using eBPF, we saw that kernel safety is very important and something that is guaranteed. As Dushyant showed you, if you don't have those bound checks, your code won't run. If you don't do memory checks, your code doesn't run. Oh, sorry. The kernel API changes are also easier and more portable when you have a technology like eBPF in place, because it provides you enough helper functions to write a code which internally could refer to different functions when you are moving from one kernel to the other. eBPF code has richer tooling. We could have talked. I have some slides about how BPF trace, what BPF trace is and what it does. But it's in short, what it is, it's about creating an API. It's about creating an interface where you can easily converse with the kernel via your BPF. So if you remember the first set of hands-on that you did today, where you were doing the exec snoop and all, there you didn't write any code because all the functionality, all the code was already written, and you had a very simple command line: just do an exec snoop with the rest of the arguments, and it would do whatever you are. It would start snooping on the executing process right now. Now, considering everything that we have talked about till now, and I guess yesterday when you guys were studying about Kubernetes as well, eBPF and Kubernetes kind of go hand in hand with each other. What we have Linux kernel in its current shape and its current form, it is the ideal version. It is moving towards being the ideal version of how you would want an eBPF powered virtual machine to work. That is, you can have additional superpowers added to it as and when required. But then because it's a micro kernel, you have all the requirements which are basic bare minimum requirements, but anything extra you can have an eBPF module to attach everything else to it. The definition of microkernel is what we have in here. We have the tiny core kernel with user definable kernel functionality in eBPF. Instead of having separate kernel modules, because they make the kernel bulky, and I know this is not a security talk, but as the code base in any software, including a kernel, increases, more are the bugs and more are the exploiting options in there. Obviously, when it's smaller code base, you have fewer security bugs and fewer kernel crashes because it's more vetted. Drastic reduction of static feature. Again, these are quite obvious things that are written in there. It creates better resource efficiency, and Kubernetes then ships custom BPF tailored extensions to optimize needs for user workloads. If you think about it from a user point of view, you don't always require all the functionalities that a kernel provides. But in the current scenario, it might not always be possible to remove the stuff which you don't require. What we are moving towards with eBPF and the Linux kernel is a scenario where we have a small microkernel, as they say, and with only the additional functionalities which the user from the developer point of view requires. And we are getting there, hopefully, very much inside soon. We have a small tweet there from 2019 which says BPF will replace Linux. So we don't know if that would be possible, but in the context that I just discussed it would very much be helpful for everybody involved in the development, in the deployment, and in the using process. Okay. I have about 15 minutes, so I want to quickly go through things. This one slide, which I was quite excited about initially, when I thought I will go through each of these applications, because we've talked about eBPF since morning. We have seen it in action. We see what the power of it is. But is this just theory? Is this just something that somebody created, and yes, it's a good thing for academic projects, but do we really eventually want to use it? The answer is yes. The answer is yes, and the answer is a vehement yes, in the sense that there are more and more applications which are continuing to use eBPF. There are more and more applications which are using eBPF that were not really in ways that were thought before. So there is a scope. So if you're learning things today, it's definitely something that you would use, and there are a lot of usage opportunities there. Before this, I want to show this. This is a slide that was there in one of the first sessions as well. If you see the first row there, it says that there are three major use cases of eBPF that have been thought about. Okay, so you have the networking, you have security, and then your observability and tracing. Now, if we go back to my this slide, which just has the list of applications like production deployed systems right now with eBPF, you can see that they deploy one or more aspects of the eBPF functionality that it provides. So we have BPF trace, which is actually a tracing language. If I have time, I'll probably go through it as well. In terms of, it provides a very sleek API to trace network packets. So everything that you guys were writing today in terms of exercises, I believe BPF trace can have a really sophisticated way of getting those things done. The next really relevant piece of code that uses eBPF is something called Suricata. Anyone here heard of Suricata before? It's a very interesting name, I must say. No? Okay. So what Suricata is? It's at the very basic way, it is an intrusion detection and intrusion prevention system. So it uses eBPF to to capture packets and do its analysis in order to understand, in order to infer if the current set of packets that are being received by a given system, are they an intrusion event? If yes, then it moves to its next part, which is the IPS, which is the intrusion prevention system. So it does the security part of it. The third one is BCC. I believe we worked through BCC in the morning, so we can skip through it. Cilium is also something that Dushan mentioned in the morning, so I'll skip over it. Then we have something called Falco. Coming from a security background, Falco is something that was very interesting to me, because what Falco does is, you have an application running on your system, and all Falco does is it would keep on analyzing how your application is behaving. Is the behavior according to what it should be? And how it does it is, it uses eBPF, obviously. It uses eBPF to understand the details of what are the system calls being made, what are the function calls that are being made, are you sending more packets than what is expected, are you receiving more packets than what is expected, where are you getting this information from, where is the data from. So it collects all this information in a seamless and a resource optimal way to analyze if the behavior of a system is within the bounds. Bumblebee is a development platform. It uses eBPF. I mean, it's developed in eBPF, and it helps in eBPF development as well. So it's eBPF for eBPF kind of stuff. Catran is a load balancer. It's widely used. It's a Facebook tool. It's widely used by them by deploying them in their data centers in order to perform load balancing across their multiple application servers there. And the last one, which is what I wanted to talk the most about, is NetObserve. NetObserve is what we have been working on. It is a production level system by Red Hat. It does flows and packet level collection and analysis. And if time permits and if things work well, I'll probably show a quick demo of what eBPF does as well. Okay, because I don't have a lot of time, so I won't really go through how BPF trace and Catran and all these work use eBPF, but I'll quickly jump to NetObserve because I really want to show you guys this demo. So we've seen this diagram, this visual just few slides back, and we see that we have different projects here, right? We have eBPF projects like Catran and BCC and Cilium, which are in one domain. Then we have a good number of languages, including Go and Python. They provide these SDKs or APIs which make eBPF development really easy, which fall in here. And then you have the actual eBPF runtime, the kernel runtime, the part of it which runs inside the kernel and supports the ongoings of it. Okay, NetObserve, the tool that I'm talking about, actually runs across the two spaces, from user space and kernel. So basically what it does is it captures some information from the kernel, sends it to user space, collates it, and eventually sends it to wherever the analysis has to work. How it works, what it looks like is this. This is a very simple very simple way of expressing what NetObserve is. But if you see what, okay, if you guys, I'm sorry, I probably should not have kept OVN cube there, but just imagine it as a VM where some workload is running. We have the NetObserve observability operator, which is there which is there around here, which configures your virtual machine and then is deployed on the flow, deploys the flow collector, so that all the information that it is collecting from the kernel point inside the VM eventually is collected, processed, and then done. In our case, we store it in Grafana, but whatever needs to be done. The internal structure of NetObserve looks something like this. Don't have a lot of time to cover what we have. But as I said, NetObserve is something that works across two different domains within the ecosystem that we saw. We have the kernel module of it, which does the collection. So if you see here, we have been talking about packet collection, packet processing and everything since the morning. So the packet collection part and where the packets get stored, which is one of the maps, the maps that you were building upon, that part of it happens inside the kernel. While once this collection has been done, it is transferred to the user space, which does the collation, because because we don't want we want only the bare minimum functionality from within the kernel. So all the handling, the actual handling of the packets or flows happens within the user space. So when we were designing, when NetObserve was being designed, we have really clear separation between the user space and the kernel level module of it. The kernel level module that we've written is written entirely in, it's an eBPF code, so it's written in C. Our user space code, in our case, we've written everything in Golang. Okay, so given that I have 10 minutes, I'll quickly try to. Achha, yeah. Is my screen visible? Should I increase the font size? Okay. क्या हो रहा है? Okay, fine. Okay, so initially I planned for 2 separate demos, but in the interest of time, I'll just do one. So in order to, before I go through to the demo, there's one thing. So what I'm trying to demo today here right now is the packets capture demo. So what we've specified is that this is my system, this is a VM on which something is running. As an observability operator from NetObserve, what I require is just collect anything that is running on running protocol TCP on say a port number 80. So anything which is HTTP in our case. Okay, we do have a proper CLI and where you can push in buttons and do these things, but here I'll just try to do everything in everything here is. So there are a few things that I need to specify here. I want to specify what is the interface that I want my observability operator to run on. If I don't specify anything, it just runs across all operators and all interfaces, and then there's a lot of data to capture. Next, we specify some elements. Mostly the 2 important things that we need to look at are these 2. So this is just to enable the packet capture that I'm going to show you. And this is the actual filter that I'm working on. Okay, so anything which is TCP on port 80 is something that I want to capture. Now I'll just start my agent. It's now started. And now in order to see what are the packets, so if you are capturing something, you want something there to capture it as well, right? So I can capture it across in simple PCAP formats as well, but just to show you, I'll show you that I'm going to do it on using Wireshark, and this is Wireshark running on my laptop. It's not running on either the VM or anywhere else. Okay, so we are here now. Now my thing is I need to generate some workload in order for it to work. So let me do something very simple. Is this correct? Is this a valid? Okay. Okay, so I did a simple wget. What wget does is it tries to download the website there. Here it says that something happened here. Now, if you look at my Wireshark window here, where it was nothing there till now, this has received some 10 packets, one of which, but my question here is, do you think that something like, oh, sorry, I didn't realize Wireshark is not showing. Nobody told me. Okay. Right? Okay, but now I'll show it again. Otherwise, it would look as if this was there. Continue now. Okay, let me do things from the beginning then. Okay, I just started my agent and I started Wireshark. Now Wireshark is waiting on something to be sent to it. Till now nothing has been sent. And now I just try to create some workload, which is get what IIIT site has. And I get these 10 packets. So this is basically, I have created a workload. My observability agent was able to extract that workload, and then because my Wireshark running on this particular on this very laptop was the one that was supposed to collect it, it just sent everything here. Now, does anyone want to tell me for a website like iitd.ac.in, do you think it would all be downloaded in 10 packets? No? So something's missing? Anybody wants to take a guess on what the problem is? The answer is actually on the screen. And it's highlighted as well. Okay, so what was the filter on which we were trying to trace things? It was TCP/AT. AT is HTTP. Does IIIT website work on HTTP? Exactly. So now what we want to do is, what should I set it to? Very nice. Okay. So I just did this. The same thing. I need to start my collector at the same time. And I just do this. So we have this entire set of the entire file basically being downloaded here. So I know this is a very, it seems like a really naive set of demo because you can just capture anything with a PCAP, no big deal. What we need to understand here is the thing that we've been talking about since morning. eBPF is something that does this job at the XDP layer with minimal resource requirements, and we've been able to do it as a separate observer and not really residing within the same system, which makes it really usable. So I can just run it on any given system which just has the ability to which just has eBPF enabled, and we shall be able to run everything as we require. Oh wow, I still have 2 minutes. I rushed through things a bit too much. Okay, I can probably go back and show you more demos of the things that have been done. But any questions in everything that I talked about? I talked about the pitfalls, I talked about Cori, I talked about other applications that are working on it, and then I talked about this, the observability, the NetObserve agent that is a Red Hat product, and we work on it. Any questions? Possible? Okay, would you guys be interested in working more on eBPF after the whole day that you have spent with us? Okay, then it's a win for us. Okay, so I'll probably just this was my last slide because I didn't really want to go into more details of it. But I guess we are done then. Okay.
Sorry.
Yes.
Actually, guys, I just wanted to go back to one slide here, which Shachee showed with a nice tweet. This one. So eBPF and Kubernetes, the future. So the slide title says eBPF and Kubernetes, the future. I'm going to say eBPF and Linux. What is the future of eBPF and Linux? And why do we think that eBPF is a direction where Linux is moving and it will move? I started this session this day by telling you that Linux is a monolith. And changing anything into the monolith is very hard. If we introduce anything in the code, we have to go through many hoops, including learning, including talking to the maintainers. But what eBPF is providing us with these small modules like the one you have written, which counts ICMP packets, or the one which Shachee just showed you, which exports packet to any server outside, shows you that you can add any functionality to Linux very easily. And slowly, Linux kernel maintainers and Linux kernel teams have been opening up to more and more eBPF. So I'll give you an example of one paper that came in 2016. The paper's title was Linux Kernel Scheduler, a Decade of Wasted Cores, which listed the pitfalls of Linux Kernel Scheduler, how it was wasting idle cores while not scheduling processes. And see, network storage, BPF has been in network, BPF has been in storage, BPF has been in tracing because BPF started with tracing. Network is easy because so many people touch the network. Network is a fast path requirement. Storage is similar. BPF has been introduced to these things. But last year, there were some experimental patches from the Linux kernel group to introduce eBPF in the Linux kernel scheduler, which implement eBPF hook points in the kernel scheduler for you to implement custom loops or custom scheduling functions directly in the scheduler from user space using eBPF. So this tells you the motivation and the mindset that the community is moving towards, which is how do you make this big software programmable? How do you make this big software adaptable by using this technology? So this technology, whatever when you learn not just for networking, you learn not just for tracing, you learn it for Linux kernel going forward. So I believe BPF will replace Linux at some point. Not 2019, definitely it didn't, but at some point it's possible. Okay, so if you guys don't have any questions, we can end this one and we can give you the assignment for home.
Okay.
Okay. Today are present in the repository that was shared with you in the morning. So you worked on 3 sessions in lecture 2. Anybody who has not been able to do all 3 sessions, please go back, follow the steps once more, learn what you are doing, try to see what you are doing. If you are having any trouble, reach us on Slack. Otherwise, if you are able to do them, your next set of assignment is building 2 pieces of eBPF software, and these would mimic much more something like a real world software, that a small part of a real world software that you would build. So we would build one pod ingress and egress filter, which will filter traffic coming from a pod. Essentially, in our container setup, the traffic coming from container, and we will build a rate limiter. I'll just explain to you what they are doing. So the filter will be something like a firewall. What a firewall does is it shields certain servers from malicious traffic. So in our filter, what will we do? we will first set up a namespace which will mimic the container testing setup. In the repository I have given some eBPF code which implements a TC hook and has certain maps inside which load MAC address and IP address that is allowed by the program. Essentially, so your filter should do this action that it should load the map, it should look at what MAC address and IP address is allowed in the map. If the packet that your filter is seeing is allowed as per the MAC address is allowed and the IP address is allowed, it should let it pass, else it should block. It's a simple filter that you need to do. The code for the filter is present in this repo. Let me just show you that repo as well. Yeah, so go to lecture 3. There is a filter folder for the first set of eBPF program that we will build. This repository contains a README, it contains some tooling, some file, there's a make file for you to compile, there's a bpf filter.sh file for you to load and attach this filter. The make file has commands for you to install and uninstall the filter, and there is a main.go file which is something which we have actually missed during this session. This is a user space program for this eBPF filter. What does a user space program do? User space program will program the map according to the specification that the eBPF program needs. So after you compile this code and you run this program, you can pass into this map some arguments like the MAC address which is allowed at a particular interface and the IP address that is allowed. So when you are setting up this particular pod setup, you will copy the MAC address of the pod, you will copy the IP address of the pod, and then you will program that using the user space code. When you run, you will see the user space expects some arguments. Program that through the user space code in the map. Once the map is loaded, you will go and edit the eBPF program. So this is your eBPF program. The eBPF program already has much of the code including map access implemented. There are certain to-dos for you which you need to fill. These to-dos are not large. It's a small piece of code that you need to add in a larger set of functionality to make sure this works. So there are 3 or 4 to-dos in total. Once you do them, you can test if your filter is working or not. We also provide a load gen here which generates random packets with random source and destination address and random IP address, which you can execute inside the pod using the commands that we showed you earlier to see if any randomly generated MAC address is succeeding or not. So this is the eBPF filter. The second assignment that we have for you is implementing an eBPF rate limiter. A rate limiter is something that limits the amount of connections that are allowed at a particular interface. For example, this particular rate limiter will block any TCP connections larger than a configured rate coming on that particular network. So this eBPF rate limiter implements a sliding window protocol, and the sliding window protocol is already implemented for you in the code. The code for this is present in this rate limiter folder. You will open rate limiting kernel. The sliding window protocol including the configurable maps and everything is already programmed for you in this folder. Again, there are some to-dos here which you need to add. Simple to-dos like check if the packet is an IP packet, else ignore. This is something we covered today. So you already know how to do this. So there are simple to-dos that you need to do, and once you are confident that your code is working, you can again attach it to similar namespace host interface, and there is a load generator that you can run inside, which takes in a packet rate that you can send. So if you pass it burst rate, it will send more than your connection configured rate, or it will, if you pass allow rate, it will send less than your connection configured rate. So you can see if your extra connections per second that are being raised, extra TCP connections per second that are being raised, are getting passed or not. So these are the two assignments. If you need any more help, documentation or anything else on these assignments, you can ping us on Slack. But I think this is where we can end today. Any questions? Okay, thank you guys.